Hey, thank you everyone for all of the fantastic talks this entire past few days. It's been really fantastic. So we have one more discussion session before we head into lunch. We're mixing up the format a little bit today. We're not going to do the small group discussions. Instead, Jason Tumlinson has graciously offered to give us a bit of a sort of perspectives and overview of all of the things that we have learned about in the past couple of days that will hopefully sort of fuel some more discussion. So if you want to come set up here.
Yeah.
Do you want a microphone or no?
I should probably have it.
Okay, I'll give you this.
It's supposed to be next week. Okay, hello? Can you hear me okay? All right. I was asked to try to sum this up somehow. And I've never really liked those summary talks that are, so-and-so said this and so-and-so said something else. And also, it's not very fun to sit through a meeting and with the sword hanging over your head where you know you have to try to do justice to everything that was said. And it's much more enjoyable to just take it all in and try to send something back in terms of energy and knowledge. So this is not going to be highly organized, and I'm going to try to make it interactive after I do a little bit of perspective. But really, the first thing I want to do is thank you to the organizers, who I'm sure put a lot of work into this. It's very hard to organize a meeting at any size, so let's all give them a... Thanks to all the speakers. I caught nearly every talk, and I didn't see one that disappointed me, so congratulations to everybody. Occasionally, it happens. I want to do a little advertisement and give you some perspective because I started to realize recently that I'm now well into the upper half of the age distribution. So I know a few things that happened a while back and can give you a little bit of perspective on how things have been. First of all, we're doing something that's really important. Right? This is a healthy field. It's a critically important field to all of astrophysics. And if you needed a reason to hold that view, this is the summary page, the front page of the Astro 2020 Decadal Survey, where they identified 3 science areas for the next decade: worlds and suns in context, so that's exoplanets and the solar system; new messengers and new physics, that's all kinds of non-photon messengers; and cosmic ecosystems. And not only that, but the priority area within cosmic ecosystems is unveiling the drivers of galaxy growth. That's what we're here to talk about. Right? So in some ways, you could say that the work we're doing here collectively is in the top 3 for astrophysics, right? What else came out of the Decadal? And this is my brief advertisement. Of course, Decadal surveys are about identifying science, and that's important, and also facilities. So the first major facility to come out of this survey, or rather, let me say, the recommendations to come out of this survey were for a new generation of great observatories, and that spans from the UV optical through the X-ray and the far infrared. This survey recognized that that's a multi-decade, multi-generational, multi-everything effort that's going to play out over a long period of time, but that's what we call at Space Telescope and here at Chandra the new great observatory. So we're thinking about decades worth of flagship facilities extending out across the electromagnetic spectrum and really opening this subject. I just wanted to give a brief advertisement for the one that I'm working on because it's an active study by NASA. It's called the Habitable Worlds Observatory. This isn't an exoplanet audience, so we'll show you in a minute what this does for us. This is just one notional concept. It's a sort of 8-meter UV optical telescope that would fly in the late 30s, perhaps. And you can think of it as a super Hubble to search for exoplanets, Earth-like planets orbiting sun-like stars in the nearby galaxy. But the thing that really excites me, there's a whole range of science. This is called the Science Bento Box, is this stuff right here. Imagine you can put a million shutters or thousands of individual slit masks down on nearby galaxies to map the baryon cycle and emission and absorption. For instance, this is the fat mosaic of Andromeda in the back there. And this is, I think it's 400-something footprints of the microshutter device. So this is just to make you think a little bit about what data sets we might be dealing with in 15 years before I briefly recall the kinds of data sets we were dealing with 15 years ago. These are links that will take you to websites and Slack teams for this. And then Grant's not here right now, but there's been a significant amount of interest in linking the Great Observatory's habitable worlds, what went through this decadal survey as links, and what went through the survey as origins into a multi-generational fleet of flagships over the next decades. So, you know, if you're interested in this kind of thing, please engage with that effort. Advertisements done. Let's talk about a little bit of perspective. I've started going to meetings like this one as a graduate student, which would have been in the late 90s, and then as a postdoc in the early 2000s. And I've really seen a fundamental shift in the kinds of the questions that we've asked. When these meetings were new to me, they were essentially, there were two big subjects, right? If you were talking about halo gas, this is before the term circumgalactic medium was a thing. If you were talking about halo gas, you're really talking about quasar absorption lines and 21-centimeter maps of the nearby halo. And that's about it. There's probably, maybe there's a little bit of other stuff in there. But you know, I was at meetings prior to the launch of Chandra, so the hot gas in the Milky Way halo was, you know, really not characterized. So we've, over this 20 years or so, seen a real shift in the kinds of questions we can ask, and it's a much broader range of physical questions. So the ability to go out and get observations of dispersion measures of FRBs and the amazing plot of the sodium D map of the Milky Way halo from, where is he? Raise your hands. Oh, yeah, and also eat more kale. Jesse, hello. And, you know, IFUs in the optical, you know, infrared identification of galaxies at high redshift with JWST. There's just this explosion of observational techniques over the course of the last decade, for sure. And so actually, it was really interesting last night when I was thinking about what Cassie had asked me to do, because I kept coming back to this fact that this explosion of new observational data is like the river breaking over the banks and through the dam and flowing through many, many different channels. That's the image I had in my head. And everybody picks a channel and paddles their kayak through that channel, perhaps, but they're not necessarily seeing the other channels. So one of the things I want to work on in discussion is synthesizing these things. But this explosion of different observational techniques, and I kept coming back to this thought again and again. I always wanted to know, if somebody's showing me an observation of hot gas, how that relates to the previous talk I'd seen that was about the cold gas. So that's kind of obvious thing. But there are many, many areas where I wanted to know what's the underlying object or physics that we're both seeing from different perspectives from our own channels of the river. I think we have answered a few important questions, or at least, you know, one of the ways to figure out if a question that used to be asked has been answered is that nobody talks about it anymore. And one of the things that really nobody, there was, you know, a little allusions to it, but, you know, huge controversy we had more than 10 years ago was just how much mass is in the CGM, and there wasn't really a talk about how much mass is in the CGM. Michael Masseri, if he's still here, did talk about the mass budget of dwarf galaxies in his talk, but Xiaowen did this morning about the Cub sample, but it wasn't the center of the meeting in the way that it, Jess, am I right? It would have been 10 years ago, right? That would have been the source of all the conflicts. So, and just to prove to you, I know what I'm talking about, I guess, is that when we wrote the Cycle 17 proposal for COS halos, which we wrote in 2008, right? How galaxies acquire their gas, a map of multi-phase accretion and feedback in gaseous galaxy halos. We haven't really answered that question, how galaxies acquire their gas. There are many, many details having to do with cold clumps and filaments and the way they all interact with each other. But where that led us from this was a census, counting stuff, adding up mass. And then we did that, and other groups have come along over that time and used their own techniques, and I think that question is sort of receded into the background now. So part of the perspective I'm trying to give you is not that's sealed and signed and delivered, but when you see the focus of the questions people are asking shift from one thing to the other, you get the feeling that that things have moved on, and that's also a sign of a healthy subject. Related to this is that that census is it's a sort of a counting or weighing exercise, and you do a lot of observations and modeling and try to get to an answer that says there's this much hot gas and this much cold gas and this much warm gas, and sometimes you argue over definitional things. We've done censuses of baryons, we've done censuses of metals, and you've seen all that. But one of the really the other gratifying things is a move away, a shift, sort of a vibe shift or a terminology shift away from the kinds of phenomenology we used to do. I'm embarrassed to even remember some of the models we used to apply to CGM gas, because it was like, here's an isothermal sphere, and things are a lot more sophisticated now. And so the shift towards physics, and if you didn't see this happen, you wouldn't notice it, but there's a lot more physics in the talks I heard this week than there was physics in the talks I heard when I was a postdoc or a student. And maybe the older folks in the room could tell me whether that seems right or not, but they're probably napping. So I don't know how that strikes y'all, but those are my impressions of this meeting. That the shift has the interesting questions as judged by what people choose to work on and what they choose to give talks about and what they choose to do after they walk away from this to go and pick their next project. All of that seems to represent a shift to me. It represents to me a shift from a much more, a much vaguer phenomenological, let's see what's there kind of broad strokes subject matter towards something that is, I hesitate to say we've reached a plateau. I would prefer not to think that. But there's a definite shift now towards addressing real physical questions asked in real physical terms that I just didn't see before. So I think I've belabored that enough. The thing I wanted to do to try to stimulate some discussion was to look at the other side of this coin, right? Because the vast array of observational techniques, which just wasn't available to us when I'm, down in the back in the Stone Age that I'm trying to remember. It has a downside, which is that it then becomes more difficult to synthesize the different kinds of observations in terms of the real concrete underlying object. Let's remember, when we give our intros and our conclusions, we're summarizing the way we individually see these complex systems, but they don't know about us, so they're doing their thing, right? And that's one coherent object or one highly structured circumgalactic medium around a particular galaxy, and it's all obeying the laws of physics and following its own path, and it doesn't have this problem, right? So it's on us to try to synthesize these different kinds of observations and the different perspectives that we all get, keeping in mind the fact that there's something real out there that defines the truth. So, I kept coming back again and again in my own thinking to, when we look at hot or cold, what different parts of the thing are we seeing? When we see the small scales, and actually the drive to small scales in both observations and theory, which you saw beautifully illustrated by Dylan this morning in the Gibble simulations, and a talk by Ananya the other day about observations, just to pick two examples. Inflow and outflow, how do they relate to each other? I'm always hung up on the metals as the tracer particles, so I'm always really concerned with how they're lost or retained or recycled in particular. So I think what we might do here is, I'd like to ask people who have focused on, and I thought about being Socratic, but I don't want to pick on people and call on them. So I will ask for volunteers. And so somebody who gave a talk about hot gas, right? About the hot gas budget of the Milky Way or external galaxies. Could you please make a statement about how your observations relate to the cold phase, or vice versa? That's how I think we can organize this discussion, if you'll bear with me. If you would like to get your pitchforks out and chase this idea somewhere else, I'm fine with that. But I was asked to stimulate a discussion, so I think this is how I wanted to do it. If we could do that by subject, and then maybe we think about small scales in both flows and reverse, inflows and outflows, metals lost and retained. And then I underlined the last thing there because I'm really thinking a lot about the breadth of the observations and how the very different perspectives that provides is both very revealing, but also somewhat confusing. So that's kind of where I want to take this. Is that okay? I'm getting lots of blank looks and maybe some raised eyebrows about this crazy idea. But can we start? Can we at least try this and see how it goes? Is there somebody who has either done a cold gas, focused on simulations of cold gas, or observations of cold small scale structure that would like to give their perspective on the hot gas results that were presented? Is there someone in here wants to take that bullet or lay down on those train tracks? Good man, hit it.
Yeah, I'm just curious, for example, if I give the simulators for observers, here's the velocity field of cold gas in the galaxy down to parsec scales. Like, this is the answer. I would like to know what that means in terms of how much pressure, mass, and temperature of hot gas is there in the immediate vicinity of these cold clouds. So yeah, that's my question to the hot folks.
Okay, so that's another good way to do it, which is to phrase it in questions. But this is what we're trying to do here, right? Is to find the places where these things connect to each other. So does anyone want to address that? Jesse was brave enough to start, so.
Someone who talked about hot gas.
Yeah.
Have a response.
You've got a three-dimensional velocity field of the cold clumps, and you would like to know the corresponding behavior of the hot gas, which is a pretty useful question if you ask me.
I don't know if I can directly answer that question, but I was going to say that I've seen some papers recently from, I think it was called the ALMA Quest survey, that looked at CO and H alpha rotation curves of galaxies, and definitely not on parsec scales, but several hundred parsec scales, and found that the rotation curves of cold gas traced by CO and hotter gas traced by H alpha differ by only a few kilometers per second, all the way out to near the edges of the gas disk. So I think I was surprised when I read those papers that the velocity curves for such different phases are so similar.
What about the even hotter phases? Do we have any constraints on rotation from X-ray? No. But you wanted to say something else.
Jonathan over here has something too.
Okay, so from observations, we don't have any constraint on the kinematics. We can right now only constrain the density and temperature. And yeah, you have to probably assume something about the velocities. That's it.
Yeah, so on the original question, so one thing I would argue that if you show that the cold gas has a very wide log normal density distribution, then the hot gas is simply not there. because hot gas would kill such a distribution. And two, if you manage to measure the rotation profile of the cold gas and can infer from that the rotation profile of the hot gas, so it likely follows the rotation profile of the hot gas, then we can understand if the hot gas is inflowing or outflowing, because these things would predict different rotation profiles of the hot gas.
Other thoughts?
I'll say one thing. When I saw the sodium map, and sodium occupies one extremum of the temperature scale, basically. It's the coldest stuff you're going to be able to reasonably detect. And in fact, I don't know, this is another historical note. I'm really getting Grandpa Simpson here today, but those were the lines that were used to argue for the galactic corona in the first place, because Lyman Spitzer was visiting Guido Munch at Caltech, and they had data of sodium lines in the high latitude stars. And he said those shouldn't be there because the clouds should last a very short time, right? So he worked out a pressure equilibrium and inferred a hot medium from the existence of the sodium lines in the high latitude stars. So anyway, along those lines, Jonathan says that the log normal distribution of cold stuff shouldn't exist that way if the hot material does. But any place where you have the cold clouds being destroyed, you better have a hotter phase present to do the destroying. And so there has to be some interaction, even if the timescales for destruction are short, and we typically don't see them. There has to be some kind of, so it's almost like they have to be together in a love-hate relationship at some level. I think there was one here, and then Jess is in the back.
Yeah, I guess from the theory side, and I haven't looked into this too much myself yet, but the relationship of a cold cloud moving through the CGM, etc., then the kind of mixing layers that we've been talking about on the outside that are potentially what we're picking up with a number of the observables that we have so far. When does that they're presumably moving together, given it is the mixing layer on the edge of the cloud. When does the hot phase on the outside, how am I trying to put this? Is that it then? It kind of cuts off and then the velocities of the hot phase are doing something else in it? Or is the hot phase also moving with the cold clouds too? When does the kind of coherence of the hot phase end? And I'm not sure we have a good answer for that yet.
Jess?
Yeah, so somebody mentioned pressure, or several people have, and I've thought a lot about this, and I don't think that there are answers yet to the pressure question, but I do think that at least when you're looking at the cold gas and observations, some of the cold gas is dense and high pressure and consistent with the kind of, very simple Malloy-Bullock type picture. And some of the cold gas, it's inescapable, is low pressure. It has to be low pressure. And all the uncertainties that you have in ionization modeling folded in, multi-component, not multi-component, any of that, you are still left with sometimes very low pressure, cool gas. People have explained this in a number of different ways in terms of, non-thermal pressure support. But I think that knowing what the pressure is of the hot gas is really fundamental to understanding what the underlying physics are. And I don't know the answer to that, but I would love to know what the hot gas people think about the pressure of the hot gas.
It's an interesting question. So let's see. Xiaowen has her hand up, and Alyssa in the back.
So in terms of interaction between hot and cold, there's that one tiny panel I flashed through in my talk. When we deproject, so especially in terms of pressure profile, when we deproject the multiple components along the line of sight with the low pressure clumps distributed at large radii and the high pressure clump attributed to inner clouds, the pressure profile we reconstructed that way is actually very much consistent with what people see in X-ray, at least in terms of the whole stack, in terms of statistical average. So granted, it's a ad hoc comparison because we're not comparing the same halos. So I think going forward, it would really be very nice to follow up on some of the nearby, X-ray detected hot halos and see what kind of cool gas component there might be, maybe with the future X-ray missions. But I want to also comment on the kinematics. So one thing I didn't have time to go over is this velocity structure function that I mentioned. Even though the overall slope is consistent with Kolmogorov, which in itself suggests a subsonic fluid. But if you look at the actual velocity dispersion, it's actually very high. It's of order 100 to 200 kilometers per second range. And that by itself cannot be subsonic for cool gas that we actually use as a tracer. So the only explanation, the only way I can make sense of the observation is these cool photonized gas is being pushed around by the ambient hot medium that we cannot see, which is very much consistent with what people see in ISM, I believe. So while being indirect, but I think there is implication, the clues for the presence of hot gas in the halos that we study.
You give Melissa a chance. She's
First of all, thank you for letting me join your community for a day. And
You're
I'll
welcome
give,
to sit down.
I'll give you. No, my back is killing me. I'll give you. I'll give you an ISM perspective just to follow up on what Xiaowen said. And so this field, in terms of the resolution of the observations and simulations, is catching up to the ISM. But as the resolution in the cold, hot, warm, et cetera, ISM has gotten greater and greater, people have been very obsessed with your third line on this slide, the sort of small scales and bulk flows. And so I would say that part of the answer to these pressure questions and all of the rest of it is resolution and size scale and what question are you actually asking. And so in other words, on really large scales, I think, kind of smooth pressure profiles and halos and whatever, all fine. But on very small scales, what's happened is that you see, as you increase the resolution, huge amounts of mixing between the hot, warm, and cold phases. And so the idea that there are these blobs with kind of onion skins around them is just totally wrong in the ISM. And so I'm not saying that the same thing is going to turn out. I'm not saying anybody's assuming that about the CGM, but there are some simplifications that are probably going to turn out to be wrong. And so I guess what I would say in my grandmotherly way, okay, would be that people should be very careful when they talk about pressure. Are you talking about the pressure in a really tiny thing, or are you talking about some, big profile on some huge scale? And I
Everything's a
think it's a
function of
different
scale.
question depending on the scale you're talking about.
Good point. Let's see, I think Andy had a hand up, and then maybe we'll move to the next thing on the list.
Yeah, just had a comment on this hot and cold gas question. I think we should just remember that observers always see snapshots of what the gas looks like. So observers are really doing weather, right? You can go out and say the Milky Way is cloudy today, but that's not telling you the climate, right? It's not telling you if anything is changing. And I think that's where I see some of these simulations. I'm blown away, but I'm also kind of scared by it. Look how these clouds are growing, fragmenting. What's going to happen if you come back in 10 million years and look at it again? They could change on fairly small timescales. So in terms of what happens to a lot of the gas we observe, that all that change with time is really important. And I think that's where the observers have to look to the simulators and learn about what's going on, what's going to happen to a lot of these weather
That's a really
clouds
good-
that we see.
Really good point. Maybe we'll finish with Stern and then move on to.
Yeah, so just to comment on what Jason said and on what Jess said. So I think the Spitzer argument makes a very strong point about that there must be hot gas in the Milky Way CGM, in the inner Milky Way CGM. But I don't think you can extrapolate from that to other galaxies. So it's not that just to get magnesium-2 you have to have a hot gas, because the argument doesn't include turbulent pressure. And the point is that non-thermal pressure, such as turbulent pressure and other stuff, can also make the cold gas dense enough to create magnesium-2. It will probably look very different than what we see in the Milky Way, but I think it's consistent with the observations of external galaxies. So I think we should keep in mind the option that the hot gas might not exist everywhere. Yeah.
I have no problem with that. So I don't know if that was already a pretty rich discussion. I don't know if I can summarize that, but you know we're learning so much from all sky maps, very high resolution studies of the cold phase, which we're not able to do in the hot phase yet. That would be maybe the biggest picture item. So I obviously just told you I hope for new great observatories to help fix this problem, or other X-ray observations that can come along. And in the meantime, we have to. I really like Andy's comment about remembering that these things change over time. So a snapshot of our Milky Way that doesn't line up with any particular simulation. It doesn't tell you one is wrong and the other right, because if you looked at a different time, that you could get a completely different result. So the next thing was small scales versus bulk flows, and we've already kind of addressed this, but rewinding the clock a little bit, like I've been doing, in the 2010 timeframe, many of the talks at a meeting like this would have had to do with hot accretion and cold accretion, and whether cold accretion was in fragmented filaments or small clouds, or whether hot accretion and cold accretion had anything to do with each other. And I was actually a little bit struck by the near absence of that kind of material. Everybody's really focused now, or many people have really focused on the characterization of the small scales, the behavior of the small scales, and I hope we can talk about the relationship of those things to larger scales, but I didn't see a lot of this old debate about, to put it in the proposal terms, how galaxies acquire their gas, in what form does that take? Maybe that's an accident. But that's kind of what I meant by bulk flows. So think about large-scale filaments falling into the galaxy and joining the disk. We did have an interesting talk on the first day about cold slow and cold fast accretion that I thought was really cool, because you see you still here? Yes, that was great. So the difference being that the slower stuff has to spend some time waiting in the disk before it gets to the star-forming region. So that's the kind of thing I'm talking about. I'm not saying it wasn't absent, but the sense of the debate felt very different than it did a while back. And so maybe we have to fight our way through this problem of the small scales to get back to that question. But I think it's not really resolved yet. So with somebody who, maybe you, Susanna, somebody who talked about small scales like to address the bulk flow issue or the mass, bulk mass transport, or somebody who worked from the larger scales want to work down. I'm sure people have opinions here about tiny clouds, so, and it's not just Jonathan. I mean, he'll get his turn.
Question
Okay.
along those lines. Maybe something that I've been wondering about to try to kick off discussion on this is, as we increase resolution, we get smaller and smaller things, right? We get more and more really tiny clouds, like Dylan showed us this morning. Do we think that all of these bulk flows, just as we, keep looking at higher resolutions in either observations or in simulations, are really just fragmenting down to, smaller and smaller scales? Is there any sort of bottom limit to that we can call a bulk flow, that's not just going to fragment further?
I know y'all aren't shy because you talked on the last subject, so.
I'm a latecomer. So someone tell me what the difference between, what scale are we talking about with the inflows and outflows? Because if I'm looking at galaxies, right, in particular if you're considering environment, that's going to actually impact how much of the gas that can be inflowing. So when maybe a better or a clearer or distinct definition of what this. Sorry, I'm not being particularly articulate, but.
No, it's fine. I mean, bulk. When I'm thinking about bulk flows, I'm thinking about large-scale things, at least 10 kiloparsecs, out to the filaments from the IGM. So that scale.
So that's funny because I would consider that small scale. So that's why I'm asking what the
One
definition
person's
is.
low redshift is another person's
Right,
low
right.
redshift.
No, but seriously, obviously at higher redshift, that's also a question because the resolution physical scale is not going to be of the local universe, which is very advantageous. So, can someone then, when you're asking this question, are you talking about this sort of nominal 300 kpc border, or are we talking about something that's more flexible? That's why I'm looking. I'd like a little clarity.
Well, my point of view is drawn from what happened at this meeting, which is most of it was inside RVer, and when we were talking about small scales, just through the bulk of the talks that address that, we're talking about things at the scale of a kiloparsec that have, or less, that have formed some way or were ejected from the galaxy or formed out of the local CGM. Obviously, there are questions to be asked about how gas gets across the virial radius. We did have some discussions about that at the cluster scale. And the quenching of galaxies near the cluster edge. So even though we didn't talk a lot about the largest scales, those are clearly relevant for setting the conditions that this happens in.
Yeah, and I was kind of thinking one thing that we was kind of sort of mentioned on the first day a little bit that we haven't talked about too much is kind of on the largest scales, the kind of bulk, how much of the CGM do we chuck out to large distances, which has quite a lot of implications for cosmology, among other things, which it's unclear, I think, to me at the moment, how the small scales affect that kind of directly, and it kind of comes back, I guess, to the accreting gas from the IGM still has to get through all of this mess before it gets to the galaxy. So I think there's a lot of work to do there for how much of the CGM is pushed out to large distances, and in terms of the metals, how far out they're chucked to, and then the relationship of that with the kind of accretion that will fuel the future star formation as well.
All open questions. Jesse's been about to jump through the ceiling, and then Dylan has something to say.
No, it's just the coffee, yeah.
I think it was Sanch. We heard something about there being chemically homogeneous, low metallicity H2 regions in external galaxies. So that very presence basically rules out the fact that all accretion flow fragments to nothingness towards the disk. Because if that happened, all the gas will, all the low metallicity gas are going to be little droplets and cannot form a homogeneous clump or cloud. And also in the Milky Way, we do see high velocity clouds that are a few kpc away from the disk. So clearly, unless between 2 and 0 kpc, you just destroy everything, there are intact, non-completely cloudlit things that are touching the disk. So at some point, I think an important connection between the simulations and observations has to be, observations do set a minimum floor to, after which you cannot destroy a cloud under an AU. We see we see things that are homogeneous on those scales. So what sets that floor in simulations, and what physics do we learn from it, I think is a very question that I would like to ask.
It's a good one. You got an answer, Dylan?
No. But as someone, so I talked exclusively, I'd say, about small scales in my talk, which for me means sub-kiloparsec, roughly speaking. But I think we have to address this question. It's not clear to me at all that this small scale, very small scale physics and phenomena matters at all for what I agree is the main question, which is this: how do galaxies get their gas? Question. So, particularly for the simulators, I think we have a responsibility to show if small-scale physics actually matters for the growth of galaxies, and that's totally open right now. What clearly does matter is the bulk flows, and I'm also struck by, we don't really talk about cold streams or cold filaments much anymore, which that's okay, but I think
you know what I mean, right? 10 years ago, that would have been the whole.
That was the debate.
Yeah.
To me, this is one of the most striking predictions from the simulation world. This is how I would phrase it. The galaxies are perhaps fed by stream-like flows of gas, and it's never even yet observationally really proven, right? Yeah. So I talk to observers a lot who are very worried about finding accretion and finding inflow, finding the gas which fuels galaxy growth. And I think it's very hard, possibly impossible, right? So you have an absorption feature. How do you ever really show that that is accretion that's going to fuel future star formation? So I think we should talk more about that and how we can do that.
Yeah, that's a good point. So on your point that we don't know if the small-scale structure matters yet, I think that's true. It has to be demonstrated. We don't get to just assert that it is important. But I do wonder whether it represents like a signal about something else that's happening, right? Is the existence of the small-scale structure in the simulation indicative of the amount of energy that's been injected, or the way that energy is being processed, or are they indicators for something that's more fundamental in a way that we could use them, even if they're not carrying most of the mass? I find that fascinating.
I just want to use my privilege of holding the microphone at the moment to throw in that there has been some analytic theory work mostly in galactic outflows showing that there is an effect on the bulk material of having small clouds being sort of ablated into the flow. And most of that effect just comes from the fact that you're like mass loading the outflow by having all of these sort of small cold clouds that can get destroyed and sort of mix into the hot flow. And there's also a momentum that gets added into that as well. So maybe that's one way that you can have the small scales affect the bulk flows a little bit. Probably not going to be a huge effect. I think I agree with that.
Just to counter Dylan's point, observationally, we have shown that for galaxies, when you have energy injection or momentum injection, small scale, not that parsec scale, but star cluster scale do matter. We have seen that there is huge variation in energy flux and momentum flux in single galaxy, when you are injecting outflow, feedback into a galaxy itself, which again, as Cassie alluded, will have an impact on what clouds survive or how you might prevent, bulk inflow, etc.
But in the spirit of synthesizing discussion, right? You two just gave us a different theoretical and observational perspective on small-scale structure. But one of the things I'm driving at here, the broad themes I'm driving at, is: are we talking about the same scales when we have that conversation? Are we talking about the same kinds of galaxies at the same time in their evolution? I mean, how much of a direct comparison is that? It may be that there's no tension there physically because we're looking at different things, right? So that's just, I don't know the answer. It's just something to consider as we go off and decide what to do next.
Also to add on this, so what why the small scales can matter is how metals are loaded into the CGM, and and it's also related to this debate about preventative versus ejective feedback, right? Because if feedback isn't preventative, then you need to load a lot of metals into from the ISM into the CGM to explain mass metallicity relation. Yeah. And to do this, the structure of the ISM and the CGM, where the metals are injected, is really crucial.
Actually, this reminds me about the most annoying thing I heard this week, which is the result, sorry Jess, about all the carbon-4 being close to the plane, and there were other arguments. Andy made some about the HVCs being close to the disk, and you in particular, Jess, had this plot where the column density distribution of carbon-4 just plummets off the page, and the external galaxies are all over here. And if you extrapolate, they're wrong by many orders of magnitude. That bothers me a lot. And I can't make sense of that because a number of people have already done calculations. Yang Zhang had a paper with Foggy where we called Maki Wei, where she looked at the amount of distant gas that could be hidden at low velocity that's just lost in the signal of the ISM. And there have been other estimates of this. It's like a factor of 2 or something. It's not many orders of magnitude. So, that leads me to say, well, if we don't have that strong an observational bias, maybe Andy's right, and we're just looking at an unusual time, and we should be thinking about the broad scope of history. But in terms of small-scale structure, which I think a lot of these small, the Loions certainly prefer to be living in relatively small things. I cannot make that work out. Yeah, you can't either. So any enterprising graduate student want to be famous, that's a problem to solve. Yes, sir?
Okay, so I want to support very much Dylan's point that, deriving observational signatures to identify the accreting gas, if it's cold gas or filaments, would be really good. But also important to remember that it's not necessarily occurring in the cool gas. So there is this mechanism that Mary Putman called quiet accretion, where the inflows are actually happening in the hot gas, where we used to not be able to see that. And then it cools out and joins the ISM only when it's already kind of indistinguishable from existing disk gas. So, and this is, for example, what Manami is seeing in her simulations that she talked about today. So maybe another way to identify accreting gas is identifying it, for example, using like supervirial gas, as Manami showed, which it's then checking whether the accreting gas actually happens in the hot phase rather than in cool phases.
So this brings me to another hobby horse of mine, which is, everybody's heard the phrase that somebody with 2 watches doesn't know what time it is, right? And I think, 6 people with 4 supercomputers have the same problem, right? It's very difficult, and I'm not suggesting a code comparison project, but it can be very difficult to know whether the differences you're seeing between different simulations are related to resolution, the underlying physics, the treatment of that physics in the code in a numerical way, some kinds of artifacts, or even just that you chose different galaxies at different times, which is like in Andy's metaphor, you're observing the weather in the morning in one city and in the evening in another, you don't have compatible measurements. So when it comes to things, and I've been thinking a lot about this kind of subject in connection with accretion, because when I look at illustrious, fire, foggy, and everything else, I see really fundamentally different behavior. We're seeing these large-scale cold filaments in foggy. There's been a number of papers from fire about how things accrete in fragments after getting hot first. And this is kind of returning to the old hot versus cold accretion, I know, but I just worry that there's still incommensurate models that makes it very difficult to compare to observations because of this effect. And I don't really want to do a code comparison project, but I would like to think about how we can put the simulations on a similar footing to make sure we're asking the right questions of each other. Maybe. Anybody else want to comment on small scale structure versus bulk? Sanch.
It's not really exactly that, but I actually have 2 points, if that's allowed. So in terms of gas getting into galaxy, I think we have observational evidence that the IGM is more correlated to H1-rich galaxies. So I think we have to think about ISM, IGM, and CGM kind of in the same sort of thought process. Most of the time, we are not connecting the ISM to the CGM. And so one of the things that I want to mention is that the Lyman alpha absorbers that we see in the IGM is more correlated to H1-rich galaxies than star-forming galaxies or just other galaxies. So that's one piece of kind of connecting thought. The other thing that I think we have really now a lot of data that we can really leverage is the kinematics. So I have focused on my surveys, but what we see is that the absorbers at really high impact parameters still have the same within the circular velocity of the gas disk, and which kind of, I think, needs more exploration. Sometimes we don't have gas information for galaxies, so this is not absolutely easy to do, but simulations can really make that a jump. And how do we translate the kinematics of absorbers to the gas disk is really probably allow us to distinguish between inflows and outflows and all that stuff. So, yeah.
Kinematics near the disk. Good. Okay, I don't see any other hands up, but we've already been getting into inflow and outflow. I think less so related to outflow, so maybe we can focus attention there a little bit. There's a lot of meetings you can go to that are more focused particularly on galactic winds and how they behave. And we had some of that, and I think all the comments I just made about comparing simulations to observations apply there, because you want to make sure you're trying to equalize the conditions that you're in. You want to have as much of a controlled experiment as you can. Who wants to take the outflow question? And you know, if you talked about outflows, if you're concerned about outflows, there was a really neat talk this morning about a fairly unique outflow, which might be two outflows that are nested together. That was cool. So would somebody like to tackle that one and give their point of view on the opposite, the converse phenomenon?
Well, I can start to ask the question since, I mean, we're looking at this from the observational perspective because, I mean, now we see that the outflow, like magnetic field traces the outflow because we see this nice co-rotation with the halo gas.
Yeah.
But we don't know actually, first of all, like when does magnetic field, like what's the condition for magnetic field that it stopped, like, you know, having this filamentary structure and it start to disrupt and disentangle with the outflow. And then what's the, like this can be answered from simulation. And also like the scale of the outflow that can be provided by the galaxy. For example, I mean, the galaxy center, of course, you have the aging and you have the central molecular zone, but in this larger scale, KPC scale, if there's some, like, can there be reproduced by simulation that such kind of structure, the foot points of the outflow can be that large? And third is, like, if we can actually measure the, like, the magnetic field in the inflow, then we would have an ecosystem. I mean, that would be very challenging, of course. But I think with these three perspectives, I'm also, and a particular question because I'm naive in this community, I want to know, for example, how different ionized phase gas convolve with magnetic field because the inflow, outflow is traced with different phases, and the ionization actually matters for the magnetic field topology and everything. So if we can get constraints from simulation, and probably from future measurements, this will be very interesting. That's my perspective.
Cool.
Thank you.
Anybody want to tackle magnetic fields and inflows? We've got 7 more minutes, so go at it. Or any other answers that, hey, there's a bold guy.
Just to say, we see a very interesting phenomena in the simulations, which is that, of course, in outflows go the metals, but also the magnetic fields out of the halo, right? So for metals, I would call this environmental pre-enrichment in the sense that then large-scale environments are polluted by the metals, and these subsequently accrete later times into other halos, especially big halos like clusters, for example. The same would happen with the magnetic energy then, right? So launched out of earlier galaxies, this would be in part of the accretion flows for subsequent growth. You could quantify this a bit in the simulations.
Interesting. Let's see, Ron Wan's got his hand up, and then in the back.
I just want to throw a question out to our simulator colleagues. It'll be great, you know, there are different codes that are being run with different feedback prescriptions. It'll be great if we have some testable hypothesis with different feedback models, you know, something that observers can actually measure and try to constrain all your models. I understand there are a lot of tuning going on to match the stellar properties, but since the CGM is not constrained, you know, even in terms of gas properties, temperature, pressure, if you would kindly put out those so that we can actually measure something and compare, it'll be very great.
That's very hard to do. Let's see, I think I saw a hand back here. I can't see who that is through the mask.
All right, Jesse's got a question.
Okay.
Yeah, on the topic of magnetic fields, FRB experts, of which there are multiple in here, do magnetic field energies affect the free electron count given some halo environment or other observable things?
Yeah, I mean, the way you would go after magnetic fields in the CGM with FRBs or any radio source would be rotation measures, and the magnetic fields are too small to detect them. And this has been done in cross correlation with like 40,000 NVSS sources. There's no signal, and you don't really expect there to be.
But does that constrain the magnetic energy in the universe?
Yeah, do you get an upper limit from that?
Yeah, certainly.
Is it an interesting upper limit?
I don't think it is, no. I mean, it's a fair question with SK and DSA 2000 where you have, say, 50 million Faraday rotation measures. Can you do something with that? But
So the FRB stuff really fascinates me, and I'm looking forward, because this should just go on and on and on forever, right? So at some point you're going to have FRBs from the whole universe so densely populate the sky that you'll end up with an electron density map of the Milky Way halo, right? It'll look like the CMB map or the H alpha map or your sodium D map. So, you know, someday there will be a map that looks just like that, but in total electrons, which is a hugely important constraint, I think, on the structure of the ionized gas and magnetic fields. And 2030? Great. All right, we're all going to meet back here. Yeah.
I did want to just add one highly speculative avenue for magnetic fields, in that there was a paper last year arguing that we can, through scattering of FRBs, potentially distinguish between, or rather, rule out spherical cloudlets being scattering sources, but that the model would be consistent with flatter sheet-like geometries that would be pressure confined in one direction. So I guess there's a chance that we could see, or if we can better constrain the geometries of cloudlets, then that might track back to some kind of simulation model that would imply a presence of magnetic fields. But that is, yeah, I'm not going to start writing proposals on that.
Interesting.
Got a question?
Yeah.
Less of a question, but on the magnetic fields thing, I think right now the FRB constraints are orders of magnitude upper limits on orders of magnitude variant simulation predictions. So I think like the part of the problem with understanding whether or not magnetic fields are important is just this lack of observational constraints. But something I was thinking about was, so Amanda showed the DM constraints on the Milky Way halo, and if we could get similar RM constraints, oh yes, Amanda, but if we could get similar RM constraints, it's a little bit more tricky because RMs are signed with the magnetic field direction, so you don't get a total, it's not the same as a DM, but you can maybe get some understanding of at least the Milky Way halo magnetic field. And similarly, I think with upcoming radio instruments, we'll start to get some better higher resolution observations of nearby galaxies in radio synchrotron. So there's some hope of maybe better constraining the very inner magnetic field, like in the disk halo interface. But yeah, I think for the outer halo, it's very hard to constrain right now.
Cassie, do we need to tie this off right at 12:30?
Yes, I think we should probably finish off. Anyone have one final word that they wanted to make there? Okay. Great. Thank you so much, Jason, for leading that discussion.
Say one more thing?
Yes.
Okay. So with my mentoring hat on, which you have noticed, one of the great things about being early in your career is that you can come to meetings like this and listen, and through discussions like this one, you should be looking for places where your work connects with somebody else's, where one of these connections pops into your head, where different observables come in. And hopefully you're coming away with the next great idea for your next paper or your next exploratory trip through the data. So that was kind of the goal of all this. I hope we met that to some degree. That's all.
Okay. Thank you. Excellent. All right. Thank you so much for that. And thank you, everyone, for coming. We do have lunch that will be in the lobby once again, but that is the end of our meeting. So thank you so much for coming. We really enjoyed having you all here, and I hope that you enjoyed it as much as we did.